Hey guys, let's solve this problem, this probability intersection linear algebra problem. So in this live, we will only focus on this problem. So let's solve it step by step. So it's asked that you have a 3 cross 3 matrix A, which has these 9 elements. And in these 9 elements, each of these elements are distributed using this PMF, probability mass function. So this is nothing but discrete uniform. This is a discrete uniform distribution which takes values between -1, 0, and 1. This is the distribution of this each of this xij. So each of the xij are following discrete uniform IID discrete uniform -1, 0, and 1. So the question is that what is the probability? What is the probability that this matrix A is orthogonal? So how to approach this problem? What is the way to approach this problem? The way to approach this problem is first investigating what orthogonal means in each of these xij's. Is there a better representation of the orthogonality? Is there a better understanding of the orthogonality? So now, when is a matrix orthogonal? A matrix is orthogonal if A transpose A is identity matrix. In this case, it will be a 3 cross 3 identity matrix, but in general, A transpose A is identity matrix. So what we'll do is we will try to express this and try to find some properties of orthogonal matrices in terms of the rows or the columns. What is the geometry of these orthogonal matrices in terms of the rows or the columns? See, if you take an orthogonal matrix A, so you have the row 1, row 2, row 3, if this is A, and A transpose, this row A transpose becomes, each of the column becomes the rows, right? Each of the column becomes the rows. And if you try to multiply A transpose A, you will get that each of the element, like ijth element, so ijth element of A transpose A becomes our I dot product of, so Ri transpose Ri, Rj. So ijth element of the A transpose A becomes Ri transpose Rj, and this is equal to I. So this is, I mean, A transpose A is equal to I. So therefore, Ri transpose Rj is equal to 1 if I is equal to j and 0 otherwise. So the problem asks you that, so therefore we can translate this problem in terms of the row vectors, or in this case the row vectors. So okay, so let's try to understand and rewrite the problem in terms of the row vectors. So observe that each of the row vectors, so understand that what's happening here, it's equivalent to saying that each of the row vectors, the collection of the row vectors, there are 3 row vectors in this case, r1, r2, r3, this forms an orthonormal basis. So what does it mean? This forms an orthonormal basis. So it means that the Ri transpose Rj, each of them, this is exactly what I'm rephrasing it, whatever the equation we have written here. Ri transpose Rj, so all the 3 of them are orthogonal, and that means 0, the dot product is 0 and is equal to 1 if I is equal to j. That means the length of the Ri's, length square, the norm square of the Ri's is 1, and all the 3 vectors are orthogonal in nature. R1, R2, and R3. They are orthogonal in nature. They're perpendicular. So now one important thing, one constraint that we have here is, let's try to understand how these rows are. These rows are written as, let's take an example of each of the row is A, B, C, and each of the A, B, C are IID. Each of the A, B, C are IID discrete uniform -1, 0, and 1. Each of the IIDs are discrete uniform -1, 0, and 1. So what happens here? There is a restriction, by the way. The restriction is that from the previous derivation that we did, is the restriction is that this vector is orthonormal. That means each a square plus b square plus c square is equal to 1, and all these three vectors are orthogonal to each other. So let's try to understand first this norm is equal to 1 condition. In this norm is equal to 1 condition, let's see that if a, b, c are randomly taking values between among 1, -1, and 0, then what are the possibilities of a, b, and c? What are the all over the possibilities? Understand total number of possibilities is there are 9 such elements. It's a 3 cross 3 matrix. There are 9 such elements. So total number of possibilities, each of them can take 3 values. So the total number of possibilities is 3 to the power 9, right? You have to find out all the combinations of xij's such that you find all the combinations of xij's such that their norm, each of their vectors norm is 1, and the vectors are orthogonal to each other. So we are trying to find out those specific, we're trying to subset it. We want to understand, we want to restrict the entire sample space to those cases where they're orthogonal and their vector length is 1. So how do we do it? First, we are trying to understand that we have seen that each of the rows are orthogonal to each other, and of course each of the rows length is 1. So we are trying to see that what are the values that the row can take so that the length becomes 1. So a, b, c can take, understand, -1, 0, and 1, and a square plus b square plus c square is equal to 1 because their length is 1. And observe that this can only happen if there are 2 zeros and only 1 non-zero element, right? Because for example, let me add a page here. For example, 1, 0, 1, 0 can be one of the solutions. 0, -1, 0 is one of the solutions. But 1, -1, 0 cannot be a solution, right? Because here you can see there are 2 non-zero 1 elements. So its square will be √2. The norm will be √2. So therefore, the only possibility that you can have where the first we're trying to count the possibilities. First, we are trying to count the possibilities where the norm is equal to 1. And the possibilities can be only of 3 possible cases where it's x 0, 0, 0, y 0, or 0, 0, z, where this x, y, and z, they belong to -1. They are non-zero. They belong to -1, 1. These are the only possibilities. These are the only possibilities where the vectors, each of the row vectors, there are 3 row vectors, right? Each of the row vectors can have norm 1. This is the only possibility. This is the only possibility. But there is another restriction out there. The second level of restriction is that they are orthogonal. And if you observe carefully, that there can be, for example, this kind of value 1, 0, 0 and -1, 0, 0 cannot be orthogonal because their dot product is -1. So there are 3 vectors and they will be orthogonal to each other. The only possible cases are that each one of them, there are 3 row vectors, so each one of them, one will have this, one will have this, another one will have this. So we have to, for example, this is one possibility, 1, 0, 0. The next one can be 0, -1, 0. And the next, another third row vector can be 0, 0, 1. Another possibility is -1, 0, 0, 0, 1, 0, and 0, 0, -1. These are a few possibilities among all possible options. So we have to therefore count that how many such x, y, and z exist, and also what are the permutation and combination of that. So there are 2 things here. So 3 to the power 9 is total number of cases, as we've already discussed. So the first option is, so there are 3 possible cases that can happen: x 0, 0, 0, y 0, or 0, 0, z. And each one of them should be assigned to one of the row vectors. So there are 3 factorial ways of there are 3 factorial ways of permuting these 3 possible cases. So 3 factorial ways for permuting among which of them is a row vector. For example, this can be the first row vector, this can be the second row vector, and this can be the third row vector. Okay. In another case, it can be the first one can be the first type can be the second row vector, the next one can be the third row vector, the first row vector, and the last one can be again the third row vector. So the 3 factorial ways of assignment. So each of the rows will have only one of the assignments, and there are 3 factorial ways. So there are 3 factorial total ways to assign this different non-zero element types that we have discussed, the norm 1 types. And because this pair, that means x00, y0, y0, and 00z, this 3 combine the all possible combinations of orthonormal bases out here, the row vectors, the orthonormal row vectors. Okay, these are all the possibilities, and all of them should be actually appearing. So the final thing that is left is all of them should be appearing, and we have formatted and combined it. Let's say this is R1, R2, R3. The only thing that is left here is that what should be the values of x, what should be the values of y, and what should be the values of z. And each one of them has 2 possible options because they're non-zero elements, either 1 or -1. So there are 2 possible options. So each one of them has 2 possible options. It's 2 into 2 into 2. So we get 2 to the power 3. So total number of options is therefore, you can see that 2 to the power 3, rather you get a 2 from here, so it will be 2 to the power 4 by 3 to the power 9, and there will be a 3 above, and it will get cancelled by 3 to the power 8. So it will be the first option. But the most important thing is first, there are 2 important things that we discussed here. Number 1 is that when it's orthonormal, when it's orthogonal, a matrix is orthogonal, then what does it mean geometrically in terms of the orthogonality of the row vectors? I mean, row vectors form an orthonormal basis, and same goes for column vector. Okay, they form an orthonormal basis. And the third thing is that if they form an orthonormal basis, what are the possible opportunities of the values of those row vectors? And we have seen that the opportunities, the possibilities of those row vectors can be x00, 00y0, and 00z. But not only that, each of the x, y, and z should be non-zero elements. So they should have 1 or -1 options. So since there can be all these 3 possibilities, x00, x0, y0, and 00z should be there. So there are 3 factorial ways of permuting them into the all different type of row vectors. And this is the AND principle of counting. And we have to also select the number of options for each of those x, y, and z. That is 2. Each one of them has 2 options, 1 and -1. So it becomes 2 into 2 into 2. So 2 to the power 3. And the permutation, that is 3 factorial. So it becomes 8. So it becomes 2 to the power 4 by 3, 8, 2 to the power 8. You have to understand that this cannot be easily generalized to n dimension. The reason being, here, we are using the very important fact of 1 square or -1 square is equal to 1. So that's the tricky part here. That's the tricky part here, that this can only be done and written and solved for 3 dimension. It cannot be generalized right now to n dimensions. So if you think in n dimensional format, that can cause you an issue if you try to generalize it and then solve it. So I hope you enjoyed the solution. I will see in the next video. Let's see if there are any comments of the students. Any comments from the students? I don't see any comments for the students. So you can watch this live, the whole recording on YouTube also. This has been recorded on YouTube also. So I hope you enjoy the solution. Feel free to ask your questions in the comments, those who have joined late, and I would love to share my views on that. And I will see you in the next video. Thank you. I hope you enjoyed the problem. We will be regularly solving live problems like this. It will be streamed both on Instagram and the YouTube also. So on YouTube, it can be better for your view. So feel free to check out that. All the best, and I will see you in the next video. Bye-bye.